Okay, I don't have any big details on this. This just came out today, as a matter of fact. Yeah, on the 9th of March. Now, they're talking about creating a petawatt of power, which is a bazillion watts, in an instant by smashing electron beams. Well, we did this. Now, this is physicists at SLAC, National Accelerator in the U.S., have shattered the record for most powerful beam of electrons, cramming an ultra-high current of around 100,000 amps into an instant. Amps are just a number, a quantity. All right, now here's what they did. The team's new technique for steering the millimeter-long chains, I'm sure they're using some kind of venturi, probably with a field effect, but their new technique for steering these little chains of electrons along a magnetic track, see, they're using magnetism, to squeeze them, crush the fields. It was just exactly what we did. The race down into a photo finish and delivers more than a petawatt of power in 1 1,000,000,000th of a second. Instantaneously, they explode into just gigantic amounts of energy. Let's read it again and think about this carefully as you read it. This is, they call it their team's new technique, is to steer these little electrons along a magnetic track that allows them to squeeze the race down, squeeze it down into a photo finish. Zzz, bam! That's when it explodes. And it delivers more than a petawatt of power in that 1,000,000,000th of a second. I have shown that we did that exact same thing. We steered it and squeezed it right down into the tiniest little orifice, and it exploded exactly like they say. Well, okay, my friends, I am excited. This is fabulous. I'm just going to let this play. Watch what they have to say about using this particular invasive light to bounce back, and they can see the transition metals, which I've been talking about forever. And from that, they can determine what this mouse basically looked like. And I have to agree that what they're doing is what I've been talking about. Now here it goes.
For example, a group of paleontologists were able to retrieve the color pigments from the fossil of a 3 million-year-old mouse.
Well, first of all, I don't agree it's 3 million years old, but that's okay.
By scanning the fossil with intense X-rays, the fossil will emit back X-rays with different characteristics. All
right, this is where we are getting our transition metal bounce. Every different type of metal, and well, every different type of molecule, an atom, has a different bounce. And that's the light, and that's the frequency of the light. Hold on. All right. The harder the substance is, the harder it's going to bounce and come back quick. If it's a pillow-like thing, it's going to bounce and come back slow in the red region. If it's very hard, it's going to bounce back fast. Basically, that's the difference in colors, is how hard it hits. We're using the same light to hit here, and why is some of it coming red and blue and green and so forth? Well, the reason is the hardness of what it's hitting. That's basically all it is. All right, so let's continue on with this.
The study of these X-ray emissions allowed scientists to determine what type of metals were found in the fossil. And by identifying these metals, the team concluded that this 3 million-year-old mouse had reddish fur. This type of discovery could teach us a lot about evolution in distant times.
Now,
These
don't
X-ray
forget,
emissions allowed scientists to determine what type of metals were found in the.
This is what I've been showing forever. These are transition metals. This is what your body runs on. You have to have these metals in your body. Now, this is interesting to see where they are accumulating. I'd like to see it all in one shot, but this green is, you know, you can see the outline of the body. Is it blue? Hold on.
And by identifying these metals,
it looks,
the team can.
Yeah, all right. So it looks like the bones if I'm right, if that's the bony structure, the back and everything, and the tail, which it does appear to be, that's blue. Now, what does blue represent?
That this 3 million year old.
Watch. Let's look at it again. You got to keep looking over and over at things before you really understand.
These X-ray emissions allowed scientists to determine.
All right, so here we go. You can see the pattern of the bones. All right, now, they will have a certain color, and it seems to be blue.
What type of metals were found?
You see the blue on the bones? Watch up here, watch the tail around here.
Found in the
You see it? Now let's watch at the back.
fossil.
You see it? So something, there's the leg, and the tail will have the same blue. So,
And by
we know the transition metals carry things around the body. Well, what is that blue doing? Well, the blue is some transition metal. Hold on one second. Let me just show you where they are in the periodic chart. These are the transition metals, this blue section here. Something there wants to bond with probably calcium or something that was in there, in the bone. And is it just this one? Because it depends on what this was entombed in, what will invade and stabilize. Sometimes it won't always be the blue. It might be a green or a yellow color that shows up because the blue just wasn't there, or the chemistry that was in here was washed out with salts, acids, whatever, and then it became a different substance than normal bone, which would take on a different color than the blue, maybe yellow or whatever. So there's a lot to consider here, but you can see it's quite obvious those were the transition metals, and they accumulate in certain tissues. But the tissues can be different tissues, even though it's the same body part, and it's the bone. One could be a lot of calcium, one could be almost no calcium in it. I have bones here, like this one right here. There's no calcium whatsoever. You'd call this a mud stone. It's a bone. It's like, I think probably like a wrist bone or something like that. So if this was scanned for metals, you're going to see a lot of metals in here, which are going to be the blood. Now I wonder about this heart. Let's see if we can find his heart. Hold on. Let's see. Because I just ran across this a minute ago.
Allowed scientists to determine.
Let's watch. His heart's going to be right up in here. I would assume it'd be red. I don't know.
What type of metals were found in the fossil?
I would say it got to be right up around in here. Maybe it's green. I don't know.
And by identifying these metals, the team concluded that this 3 million year old mouse had reddish fur.
Well, how about these creatures I'm showing? You know, let's take a look at something like that. That's different than a human, but it's a foot, and that's where the tibia comes down. It's exactly where ours would be, and it rocks in that cradle, and this side here is where the fibula comes down, the second bone. It's only held in there by 3 ligaments, and they just fall right off. We got a bunch of these. They're not uncommon. Everybody that had a foot had 2 probably. Now I got all kinds of stuff. But they're getting more and more into seeing things that they never saw before, like these transition metals. Now they're using synchrotrons to do this. It's very, very expensive equipment, and they're using high-powered particles, X-rays. The stuff I was doing and the research Rod Warren and I did together was with light, all right? Not with well, they're using light, but they're using the heavy part of light. They're just using the X-ray part, which is what's considered to be the mass. All right, it's a little different. It's hard to explain real quickly. You have to pay attention for an extended amount of time to understand dipole electron flow theory. It's not hard to understand, but you can't just snap it off in 2 minutes. All right, so what are synchrotrons? And that's how they were able to view that mouse. I'm just going to let it play here. They're high-speed particle accelerators, and they separate the white from the black. And the black is X-rays and gamma rays. It's just standard. As you get higher up and up through the frequencies, lower frequencies, you just have regular light, and visible light is in air. But here it's still light. It's not just the heavy particles. Once you get up past the ultraviolet catastrophe, it's called, at a certain point, the white particles no longer can stay with the black. The black is the mass, and it goes away, and the mass is here. These will kill you, X-rays and gamma rays, because that's nothing but mass. Back here, you had both, so this bounces off of you until you get at a certain place up in the ultraviolet where it sort of penetrates, and then up even higher, the white particles doesn't even stay with the black particle. The black particle takes off all by itself. That's called X-rays, and we're going to watch them being created in a synchrotron right now. All right, get ready. All right, this is from a place called SLAC. Here we go.
Synchrotrons are large machines like this one at SLAC. Inside this building is a metal tube that serves as a circular racetrack for electrons.
All right, I'm sure they have some kind of magnetic fields that are forcing these electrons into this tubular enclosure, spinning them around and around and around. So here goes.
As the electrons spin around, they release energy in the form of X-ray light.
All right, X-rays are the black particle. There's a black and a white one together. The white ones are very fluffy. They have no mass to speak of. The black ones at a certain speed, at the ultraviolet catastrophe, they release from the white. They go off all by themselves. That's what an X-ray is, just the dark particle. It's a heavy particle that can damage you and kill you. All right, so let's go back here a second.
Electrons spin around. They release energy in the form of X-ray light. Scientists direct the X-ray light into experimental rooms, where they can use that light to produce images of the samples they're studying. Basically, they use the X-ray light to reveal information that's too small to see with other common scientific tools. Synchrotrons are like a powerful camera or microscope.
All right, so what are they doing? How are they seeing things? They're hitting something with a bang, with a big black particle, and it's releasing energy so they can see it. Now, they have depth that they can work with. So it depends on how much energy, how deep penetration into the specimen they're looking at. All right, so remember that. We've got penetration depth, and we have the black particle all by itself. All right, so let's keep going. I'm going to jump back a little bit. At this point, they have released the black particle from the white particle, and that's all they're shooting down here is X-rays. So they're coming down.
Studying. Basically, they use the X-ray light to reveal information that's too small to see with other common scientific tools. Synchrotrons are like a powerful camera or microscope. Today, you can go to the hospital to get an X-ray of your bones. X-rays are similar to visible light, but just like infrareds or ultraviolets, we can't...
All right, they're similar to, they're nothing more than light, but at a certain point, at the ultraviolet catastrophe, it's going so fast that the white and the black separate, and you lose the white. It goes to nothing, and the black just keeps going because that is the mass. That's the ability for it to do that. Let me take off the caps.
See them. At the hospital, the X-ray beam is just strong enough to go through your skin.
All right, so the X-ray beam is just enough to get through your skin. All right, so they can see the bones highlighted in the background. If you keep pumping up that energy, it will just destroy the tissues. Now, something that they have never even thought about, and they're not thinking about now, is whenever you get a CAT scan or anything that invades your tissue like this, with a high energy, this is exactly what it's doing. There's a higher energy coming here. You got bacteria living in here. Bacteria, they're little living creatures. And as far as I'm concerned, you're irradiating them here. I'd like to know if there's any damage done to the bacteria in your body when you get a full body CAT scan or something like that, or whatever. You have enzymes in there that are created by bacteria. If you don't have the bacteria, you don't get the enzyme. If you don't get the enzyme, you're going to not have the chemistry. So let's continue here. Let me just go back a second. This requires going back over and over. So they're just getting ready to shine the X-ray.
The X-ray beam is just strong enough to go through your skin, but not your bones. And the
all right, there's your bones down in there. You turn it up higher and higher and higher, you can get... Anyway, go ahead.
camera captures the shadow of your bones. At a synchrotron, the X-ray light is a lot more intense. Using different techniques, the X-ray will scan a sample, and the light that bounces off will help us build an image or extract other information to interpret the research.
So they're not working with somebody's body. They're working with something that is just going to bounce light back to them.
So, how do we use them? One of the most common applications of synchrotrons is in medical and pharmaceutical research. The powerful X-ray light allows for high-resolution 3D imaging of proteins.
All right, don't forget, this is high-energy particles coming into your body. I'm just telling you, I would like to find out if it had any effect on the bacteria. You know, they're doing this to see what's going on in your body, and that's important, yes. But what else are you doing when you do that? Are you possibly damaging something? That's be important to see. And all this is fecal swabs of what's in your gut bacteria, because primarily that's where it ends up. That's the end and the beginning. All right, is in your gut. That's the fluid-filled highway. If you don't have the right bacteria in you, you're just not going to be able to create the proteins which build things or the enzymes which break things. Both of those have to work together to make you healthy. And if you're irradiating those bacteria, there's a possibility. I'm not saying for sure, but there's certainly a possibility you could damage them.
Like the coronavirus spike proteins, or structures like DNA and RNA. Using these structures, researchers are able to develop new molecules to interact with viruses to prevent diseases. Another application at SLAC is the study of batteries. Scientists use synchrotrons to visualize the chemical process inside a battery.
All right, that is very interesting. I would like to look into that, because a battery is a phenomenal device, really. A battery never gains weight. Never gains weight. If the battery's dead, has no energy in it whatsoever, it weighs an ounce. You just pump that thing full of energy to do a lot of work. And I mean a lot of work. Batteries can do a lot of work. You pump it full of energy, it still weighs exactly the same amount. There's no change in the weight that's detectable. Same with cars. You take a 4,000-pound car and you drive it all day long and it's empty with no more electricity. You fill it back up again, it still weighs 4,000 pounds. Never changes. Full or empty. A car, a 10-gallon tank of gas weighs 60 pounds, 60. All right? And you go about the same distance as a fully charged electric car, which never uses any weight whatsoever. This is what I'd like to see about what happens inside the battery. How the electrons are accumulated in there, because it's only white that you're putting in there. The white has no mass. It's only the white separated from the black. I think I've shown you. Absolutely, you will see it. This is pretty fascinating for me.
Can look at how the repeated charge cycles affect the physical structure of the battery and how it reduces capacity over time. Little by little, they're able to identify manufacturing processes that will improve the efficiency of batteries. In another example, a group of paleontologists were able to retrieve the color pigments from the fossil of a 3 million-year-old mouse. By scanning the fossil with intense X-rays, the fossil will emit back X-rays with different characteristics. The study of these X-ray emissions allowed scientists to determine what type of metals were found in the fossil. And by identifying these metals, the team concluded that this 3 million-year-old mouse had reddish fur. This type of discovery could teach us a lot about evolution in distant times. In summary, synchrotrons can reveal secrets that the human eye or other common scientific tools wouldn't be able to see. So, synchrotrons are really an important tool for scientists.
All right, this is fabulous. And what they're doing is accelerating light and separating the black from the white. The black is the X-rays and gamma rays. The white is the energy. And at a certain point, the ultraviolet catastrophe, the white just cannot keep up with the black. And the black just takes off and is stripped away from the white. All right. Obviously, you know that different light has different energy. The more light you have is obviously more energy. Now, this is light, all right, and this is the way light comes in, the wavelength of the light, which is the distance between the spin. And it is spin. It's not what they claim it to be, like a flappy wave. It spins just like that. And the particle is on the end and it spins. If you looked at it from the side, you'd see it as a wave, yes. It looks like a wave, but it's a spin. So it's spinning and spinning and spinning and it's spinning, and because the black and the white are together here, the black has mass. The white has no mass. It's just tagging along with the black. At a certain spin, the black just takes off, and the white drops down to nothing. There's no more white left with it. So it's spinning, spinning, and you would expect it to just keep going like this, more and more energy. And they say this is the catastrophe because everything just drops down to zero. This is the light particles. These are the ones that give you the light. The black particle just keeps going forever, and the white one drops to nothing. And the black one is what ends up smashing you and causing, gamma rays and X-rays and all that. But the white, the energetic particle, just falls off. That's the ultraviolet catastrophe. Now, only dipole electron flood theory solves this. It says it's the ultraviolet catastrophe is the error at short wavelengths in the Rayleigh-Jeans law. When there's no law that works. None of these laws work because they don't even know how the dipole electron flood theory works. Until you understand that, you can't create any laws. So it's depicted as classical theory in the graph for the energy emitted by the ideal black body. Well, it doesn't work this way. The faster it spins, the more energy it gets. All of a sudden, at one point, only the black is left and it takes off by itself. The white, it just stops being tagged along. It's gone. All right, this sums it up pretty good. In practical terms, the classical equation predicted that the energy rated by the black body would become infinitely large as the frequency increased. In other words, the frequency goes up higher and higher and higher. But as you hit the ultraviolet catastrophe, you lost your energy. So it says essentially the amount of radiation in the ultraviolet and higher ranges would become infinite, more and more and more energy. This prediction was clearly incorrect and led to the term ultraviolet catastrophe because it suggested that objects would radiate an infinite amount of energy, which obviously doesn't happen in reality. At a certain frequency, you just lose all your white and all you have is the black particle left. Now, Max Planck came up with Planck's constant. Well, we have to look into that because they don't know how dipole electrons work. So you can make any constant you want and say, okay, this makes everything work, and that's the end of it. Well, no. It's like special relativity, general relativity, all these kind of different constraints that they put on things based on what they had to work with was Einstein, and Einstein just wasn't right. You can accelerate light, it's a particle and it's a wave, it's a dipole electron that builds everything there is, and you can separate the black from the white, the dipole, and never realize that could happen. They can separate, and that's when electricity happens. You pull the white away from the black. The white has no mass, has all the energy, and has to come back to the black as electricity. That's what happens, and it comes back with a vengeance. The more white you have, the harder it comes back. That's electrical conduction. This is, I don't think this is very meaningful. This is Planck's constant. Energy equals his constant here times the frequency of the photon. Well, the frequency of the photon is how fast it's spinning. Now he's multiplying this number times the spin. So all that tells you is that there are going to be certain values according to this number that are energy levels. Now, is that right or not? I don't know. To me, it's meaningless anyway. What's the difference? At a certain point, you lose the black particle, and the black particle continues and the white sloughs off. This doesn't really solve anything for me. I solved it by saying that at a certain spin, which is the frequency way up on the chart here, at a certain ultraviolet range, the black just keeps going and becomes these very hard, heavy-duty particles that will damage you and hurt you. Up to here, you've got the bounce of the white along with the black, so it's not devastating. It gets sort of invasive up in the ultraviolet, but then it gets completely destructive when you get into the X-rays and gamma rays. Hopefully that makes sense, and this, to me, does not make sense.